The focus of lesson 5 is on the impulse momentum theorem. To understand this theorem, let us consider a ball that is moving horizontally to the right, to the left, with an initial velocity vi. It's moving towards a wall. This means eventually it will collide with the wall at some point here. Now, from this observation, I can say that this part actually is before collision, is before we collide with the wall. It's when the object is going towards the wall. Now, at that instant, we will measure our time. That means on our clock, we'll have our initial time, Ti. As the ball moves closer to the wall, the time will be increasing on our clock reading. So that at some point, as the time increases, the ball will actually start colliding with the wall. Now you have to notice that the wall will start to exert a time varying force on the ball. So we're going to have what we call a time varying force on the wall. This means that the ball will experience a number of forces that come from the wall. These forces will range from a small force increasing like that until they get to a maximum force. Then they decrease again, going to a small force like that. Here we'll have the maximum force. Then they are increasing to the maximum and then decreasing again. All these forces, we then take an average of them to represent them by a single force. So basically we'll then have an average. The time varying force will give us an average force of all those forces that the ball is experiencing. And because we're taking an average of a number of forces, that average must be the net force. In other words, the wall will exert an average force, which we call the net force. It will be one single force that averages out all the forces that are acting on the ball. And it will go in the opposite direction because the wall is the one that is stopping or changing this velocity that the ball is coming with. We say it's a time varying force because here we have a force of 0. Here we have a force of 0 because the ball is not in contact with the wall. And here they start increasing until the maximum and decrease. As they do that, the time would be increasing. So the force will be varying, will be changing from 0 to maximum, then going back to the smallest. It will be varying with time as the time is going on. To understand this concept and what I'm saying, go to the previous lesson where we introduced impulse. We spoke extensively and in detail about this phenomenon. Now, because the wall exerts this force on the ball, it will make sense for the ball to then rebound and go back to the opposite direction because the wall is actually blocking it by exerting this average force. Now, it means at this stage, the ball will then go in the opposite direction and attain . and attain a final velocity, because now this velocity will be different from the final velocity. In fact, if we look at this situation here, if we consider this situation, it will be during the collision. This is when the wall and the ball are in collision. And if we look at this situation here, it will be after collision. This is after the wall has exerted a force that pushes the ball to go in the opposite direction. Now, at this stage, you also have to realize that as the ball experiences this force and it goes backwards, the time will still continue going forward until the ball is going in that direction and we have the final time, TF. This means that in the entire motion, we actually have the final time minus the initial time. And this will give us the change in time. It will tell us how long it took the ball to go towards the wall, to collide with the wall, and also go back in the opposite direction. We were measuring all this time as this force started to be zero, increased, and then went to a maximum, and then went back to zero here. The force was varying through time. Right, so this is measured in that time period. You know, if you have been following the lessons from lesson 1 to this lesson, you will realize that all the concepts we have studied, they are actually in this specific problem. We are now bringing them together, all at one place. Why I'm saying that is because one thing that you can notice is that we actually have the change in momentum from initial to final as the ball moves before collision, during, then to after collision. Because this ball here, it actually has the mass. We can give it the mass m. This means I can quantify here the initial momentum to be mv initial. And here, after collision, I can also quantify the final momentum to be mv final. Hence, I'm saying that the momentum is actually changing from initial to final. And that change is actually caused by the fact that the wall exerts a force on the ball, thereby changing its direction and changing its velocity and changing its momentum. And this happens over a certain period of time. The change in momentum from initial to final occurs over a certain period of time. That to me sounds more like Newton's second law, where we're saying that, from this Newton's second law, we're saying that the net force is equals to the change in momentum over the change in time, because we do have a change in momentum. Momentum changes from initial to final over a given time period. Now, this force, yes, we have to understand that it's an average force, as I've explained. At this stage, what I can do is that I can multiply both sides by the change in time and this side by the change in time as well. So that this side, the change in time and the change in time, they cancel each other. And I'm left with the change in momentum. And I'm going to have time times, I'm going to have the net force times the change in time. So this means this side, I'm going to have the net force multiplied by change in time is equals to the change in momentum. When we look at this equation, it's important to see that this side here is actually what we defined as the impulse. We said that the impulse is the average force or the net force multiplied by the time during which this force is applied. And it is exactly what is happening here. And here we are saying now this force is equals to the change in momentum, what we discussed in lesson 2. So essentially I'm saying that this product is impulse. We defined it as impulse, and we are saying now it is equals to the change in momentum. And we call now this the impulse momentum theorem. We call this the impulse momentum theorem, because this equation actually suggests, or it's saying to us, that the impulse of a force is actually the same, is equal to the change in momentum of that object. This is to say, if we look at this example here, when I want to calculate the impulse from the definition of impulse, I'm basically going to take this force and multiply it by the time it takes for the force to exist, right? Which is actually this side. And this actually will give me the impulse. The two are equal from how we defined impulse. But we are also saying here, according to this theorem, that if I also take the initial momentum and the final momentum and subtract the initial momentum from the final momentum, in other words, I found the difference between the two, I actually expand this equation here. If I actually say the final momentum, which is mv final, and I subtract from it the initial momentum, right, which basically is taking this momentum here and that momentum there and subtracting the two will give me a change in momentum. Even if I do this mathematics here, I'll still get the same answer that I got when I multiplied the force and the change in time. So it gives us an alternative way of finding the impulse, this equation. Now, this is a very important thing to observe, because in reality, when we do experiments, or maybe we try to calculate the impulse, in reality, we find that it is difficult to calculate the impulse using this formula, using the net force times time, because it is not easy to measure the net force, especially because it was varying. Remember, it was a force that was changing here from 0 and going back to 0. It's very difficult to quantify this or to measure that. However, it's relatively easy to actually measure velocity. We have a lot of techniques of measuring velocity. And it's quite easy as well to measure the mass. We can simply use a scale and get the mass of that object. Now, I can then now use this formula to find the change in momentum, because these two are easy to measure, the mass and the velocity. After I've found the change in momentum, then it is also easy to measure time. You can simply use a timer or a stopwatch. Then it means now I have the time, I have the change in momentum, and I can calculate the net force. So because it's difficult to measure the net force in reality, we then use other parameters such as change in momentum and the time to then calculate the net force. This theorem becomes important in that sense. The other thing that we need to observe from this theorem is that if we look at the SI units, say I rewrite this equation here to be the net force times change in time, and this side I have the change in momentum, we can see that the net force will be measured in newtons and the time will be measured in seconds. But this side, when we measure the change in momentum, is actually measured in kilogram meters per second. And this actually says to us that the Newton second is exactly the same as the kilogram meters per second. So 1 Newton second is equivalent to 1 kilogram meters per second. And you know, this is exciting to actually reconfirm, because when we defined momentum, we observed this relationship. Again, you still have to understand that impulse is still a vector quantity and the change in momentum is still a vector quantity. So the two, they still relate really well. In conclusion, the impulse momentum actually assists us to measure how the net force changes the momentum of a moving object, because really this net force changed the velocity, which will give us the momentum of this object from initial to final.